Our summary notes for Unit 4 are written in sections, and the sections correspond with the objectives and how we worked through the unit. Section 1 is multiplying and dividing rational expressions, which really boils down to just factor and then cancel. So we've got some factoring to do. The first rational expression, or the first fraction, the numerator is a difference of perfect squares. So let's factor that by x plus 5, x minus 5. The denominator of that fraction is just a greatest common factor. These two terms share a factor of 4, so we're going to factor out that 4, and we're going to be left with x plus 7. Now the second fraction, the numerator is simply a trinomial with a leading coefficient of 1. So really what we're looking at is the factors of positive 14 that add up to positive 9, and that's x plus 7 and x plus 2. And then my denominator really can't be factored because it's just x minus 5. So now the problem is fully factored. What can we reduce? Well, the 2x minus 5s can reduce each other to 1. The 2x plus 7s can reduce each other to 1. And I think that's all we've got right there. So my final answer is going to be x plus 5 times x plus 2. And my denominator is going to be 4. Moving on to the second problem in section 1. Now this problem began as division, so I rewrote it having done the first step. The first step is change division to multiplication by flipping the second fraction. So I've already done that. Division has been changed to multiplication, and that second fraction has been flipped. Now it's nothing more than what we did the first time. Factor what we can. C plus 4, that's as good as it's going to get for a second. Down here, the denominator, factors of 6 that add up to 5. C plus 3 and C plus 2. The second fraction, a trinomial with a leading coefficient that is something other than 1, which simply means I need to do a little bit of a guess and check. I know the factors right here that make 2c squared are going to be 2c and c. Now the big question is, what are the other two factors that are going to produce a positive 5 in the middle when I FOIL it? Well, there's going to be a minus 1 there, and there's going to be a plus 3 there. Go ahead and FOIL it out, and you'll see that this is what you get. Now, down here, there's another GCF of 3c. And when you factor out the 3c, you're left with c plus 4. So now everything's been factored again, and it's time to start reducing. This c plus 4 can reduce with that c plus 4. That c plus 3 can reduce with that c plus 3. And we're left with 2c minus 1. You can put it in parentheses if you want, but you don't have to. Multiplied by over 3c times c plus 2. Now the third one is simply a reduction problem. It's just one rational expression, and we need to figure out how do we reduce this. Well, let's start with the coefficients of 84 and 18. First thing I would do is I'd get on my calculator and see if 84 can go into 18 a certain number of times, and it can't. So maybe we'll have to take this the long way. Well, let's try 6. Yeah, that'll work. Okay, they can both be reduced by a factor of 6. So 84 over 6 is 14. And then 18 over 6 would be 3. Now, let's see what we've got as far as x's. When I have x cubed on top divided by x, I'm left with x squared, and it's on top. When I have y to the 4th divided by y to the 6th, I have y squared, but it's down there on the bottom. Because remember, you're subtracting the exponents. And when I have z to the 1st over z to the 2nd, I'm left with a z down there. So 14 x squared over 3y squared z. And that's the end of section 1. Section 2 of the unit was addition and subtraction of rational expressions. Now this could get a little harder because when you add and subtract, you have to have common denominators. So we started the unit with, well, what if we do have common denominators already like this? Well, that's great, because all you have to do then is add the two numerators. So n plus 2 would be the new numerator, and n squared plus 4n plus 4 would be the denominator. And now that we have the unreduced answer, now we need to reduce it, which is just a matter of factoring and then reducing what we can. So the numerator is n plus 2. This can be factored. The factors of 4 that add up to 4 are actually n plus 2 and then another n plus 2. So now that it's reduced, or factored, now we can reduce. The n plus 2 on top can reduce with one of the n plus 2's on the bottom, and you're left with 1 over n plus 2. Now, unfortunately, they're not all going to be like that. Here we have a subtraction problem where one of the denominators is t squared and the other one is t minus 1. Now, don't get confused. Those are not common t's because this t is attached in this binomial form to t minus 1. So, the actual common denominator is simply going to be the product of these two, which is t squared times t minus 1. So each fraction is going to have t squared times t minus 1 as its denominator. Now, this one already has the t squared, so what it needs is the t minus 1. We're going to take that 5, and we're going to have to multiply in the t minus 1. Now, this one has the t minus 1, so what we need to do is take that 4 and introduce by multiplication the t squared to it. Now, the next step is going to be keep the denominators. We haven't put the two fractions together yet. I need to expand this. This would be 5t minus 5 minus 4t squared. And now I can put all this together. I'd have 5t minus 5 minus 4t squared all over this. I'm going to rewrite it in descending order of the t. So I'm going to start with negative 4t squared. That's the negative 4t squared right there. Plus 5t minus 5 all over t squared t minus 1. Now, you could, if you don't like this leading coefficient being negative, you could factor out a negative from the top, which would make the 4t squared positive. But remember, it would change all of the other signs. That would make that minus 5t, and then that would make that plus 5. all over t squared t minus 1. It looks ugly, but it's the right answer. Now moving on to the next part of the unit was the solve unit. And we'll start with the easiest one, and that would be if you just had one fraction being set equal to the other fraction. Now remember, there's a 1 under that 5. It's not 5 over 5, it's 5 over 1. And now all we have to do is cross multiply. So x plus 2 multiplied by 1 is simply x plus 2. Now going the other way, 5 times 1 minus 2x is 5 minus 10x. And now let's start solving. Let's add 10x. And since we brought the x's that way, we need to take the 2 that way. And we have 11x equals 3. So x equals 3/11. Now we probably should start talking about restricted values. Remember, you can never have a 0 on the denominator of a fraction. So at the very beginning, before we did anything in this problem, we could have found out what's our restricted or our extraneous solutions. Well, let's take this 1 minus 2x and let's set it equal to 0. Because actually, we know we cannot get 0 down here. So 1 minus 2x cannot equal 0. So bring the 1 over to the other side. Negative 2x cannot equal negative 1. And then divide both sides by negative 2. So x cannot, in this problem, equal positive 1/2. And it didn't. X actually equaled 3/11. So we're good. We don't have to throw out that answer as being an extraneous answer. You can see for our second solved problem, it's much more complicated than the previous one because I can't just cross multiply. What I need to do is clear the fractions by multiplying by the least common multiple. We need to figure out what this is in factored form. It's going to make the problem really nice when we do factor it. So I'm going to factor out an n, and you're left with n plus 1, which happens to be the product of these two things. N times n plus 1 is n squared plus n. So we have found our least common multiple. So I'm going to multiply all terms in this problem. Excuse me. I'm going to multiply all terms in this problem by n times n plus 1. So I'm going to do it on this side, and I'm going to do it on this side. Now over here on the right, it's really nice. Everything's going to cancel because what was down here on the bottom is the same thing as what I introduced to the problem on top. And so I'm going to be left with simply negative 2 on the right-hand side. Now the left-hand side is going to be a little bit different. Remember, I'm distributing this. I'm distributing n times n plus 1 to both of these terms. Now something nice is going to happen. Each term is going to lose its denominator. But on this one, on the first term, it's the n's that cancel each other. And you're left with n plus 1 times 2. So that's 2n plus 2. Now moving on to the second term. On this one, it's the n plus 1s that are going to cancel each other. So the n plus 1 right here, and the n plus 1 right there, are going to cancel each other, and you're left with n times n plus 2, which is n squared plus 2n. And there's my equation without any fractions in it because the denominator's cleared. Now let's see what we've got at this point in time. I've got n squared Now I've got this 2n plus that 2n, which makes plus 4n plus 2 equals negative 2. Now if I move, I've got a quadratic going here. If I move this by making plus 2 plus 2, now I've got n squared plus 4n plus 4 equals 0. Which, if I factor this, factors of 4 that add up to 4 are 2 and 2, so n plus 2 multiplied by n plus 2 equals 0. So I'm going to get one solution because they're the same factor. So if I set it equal to 0, n plus 2 equals 0, n equals negative 2. Now remember restricted values. Let's make sure we can have n equals negative 2 as an answer. Let's go back to the original problem. That's telling us right there that n cannot equal 0. And this is telling us right here that n cannot equal negative 1. So as long as I don't have either 0 or negative 1 as an answer, I'm okay. And so it does. It looks like I'm okay. The next section in the unit was about applied problems. And the first one was work problems. This was the easier of the two concepts because all you're doing is you're taking the hourly rate of each person and then what if they work together? That means addition. And the end result is the job gets done. So we've got two groundspeople who could chalk the football field for tonight's game. One worker working alone can prepare the field in 7 hours. So his hourly rate is 1/7. You could put a 1 in front of there if you want, but we could. The other person can prepare the field in 5 hours if he works alone. So his hourly rate or his unit rate would be 1/5 of the field per hour. But if they worked together, how long would it take them to get the job done? So that's the setup. It's a pretty easy setup. Now all we have to do is clear the fractions by multiplying all the terms in the problem by what would be the common denominator, or the least common multiple, which is 35. So the entire problem gets multiplied by 35. Now, 35x over 7 plus 35x over 5 equals, don't forget 35 times 1 equals 35. Now just start reducing. 35x over 7 is 5x. Notice the fractions are going away, the denominators are clearing. 35x over 5 is 7x equals 35. So 5x plus 7x is 12x equals 35. So x equals 35/12 hours, which is approximately 2.9 hours. Together, it's going to take them almost 2.9 hours to get the field chalked. The other kind of application problem we did in this unit was average cost problems. Now, for this example, what we started off with was an initial group that we don't know how many there were, so an initial group of X friends who rented a bowling lane for a birthday party. So the average cost per person of the initial group would be 60 over X. But then something happened. 8 more friends arrived unannounced to the bowling alley and joined the group. Now what that did, they all paid their way, their fair share, so it lowered the cost by $2 per person. So that's the left-hand side of the equation, or at least the way I taught it, that's the left-hand side of the equation. Now the right-hand side of the equation is the new average cost, reflecting the fact that 8 more friends joined the group. So it's still $60. The bowling alley didn't change what they were charging them, but now there are 8 more friends than the initial size of the group, so the denominator is X plus 8. So the whole problem revolves around this equation right here. Now the next thing I would do is I would do a little trick right here. Notice 60 and 2 and 60 are all divisible by 2. So I'm going to reduce the entire problem by a factor of 2. Now that's just going to make the equation a whole lot easier to work with. Sometimes this works and sometimes it might not be the number 2, it might be the number 3. So I'm going to divide each of these terms by 2. And what that's going to give me here is 30 over X minus 1 equals 30 over X plus 8. Now that's about as good as I'm going to be able to get this problem. I'm going to have to do some ugly work from here on out. Now I'm going to clear the denominators by multiplying all terms by the least common multiple, which is X times X plus 8. So everything gets multiplied by X times X plus 8. Every single term. So it's like a big distribution problem. Now let's just take it term by term and see what happens. On the first term, the denominator X reduces with the X, leaving 30 times X plus 8. Moving on to the second term, there is no denominator at all. So I need to multiply X times X plus 8 times negative 1. So what that makes is negative, well, let's just do it the long way, X times X plus 8. Notice nothing reduced because there was no denominator. Now moving on to the third term, it's the X plus 8 that reduces, leaving just X times 30, which is 30X. Now the good news is I've gotten rid of all the fractions. There's no more fractions in the problem. The bad news is I've still got quite a lot of work to do. Let's figure out this is 30X plus 240 minus X squared minus 8X equals 30X. Let's still clean up what we can. I'm going to put it in descending order of x's. So the left-hand side has negative x squared. It also has my x's. I've got 30x and minus 8x, but they're on the same side of the equation, so I'm just going to combine like terms. So that's going to be plus 22x plus 240 equals 30x. Now I still have a quadratic, so I need to bring those 30x's over to the other side. I need to make this equal 0. So I'm going to subtract 30x. And I'm now going to have negative x squared minus 8x plus 240 equals 0. I like that first term to be positive, so I'm going to factor out a negative 1 from everything. So it's negative x squared plus 8x minus 240 equals 0. Now, I could play around with these factors for a while. This is factorable, or I could use the quadratic formula. I'm actually the factors are 12 and 20. So the factors that make negative 240, that multiply to give you negative 240 and add to give you positive 8 are x plus 20 and x minus 12. And then I've got that subtraction, or that negative sign right there. So now I'm one step away from having my answer. This is now going to give me two different answers. X equals negative 20 and x equals positive 12. Now remember what x was in the first place. It was the size of the initial group of people who rented the bowling lane. Well, you can't have a negative 20 amount of people. So we're going to throw this out as being an extraneous solution. So the answer is x equals 12. The original group was 12 people. We also had some problems in this unit where we solved for specific variables within a formula. So let's take this first one. You can see the formula, p equals 4 plus 7 times the square root of x. And right now the formula is being solved for p because it says p equals, but what if we wanted it to be solved for x? So that's just another way of saying I need to get x by itself. I need to start with an equation that says x equals. So the first thing I've got to do is I'm going to get rid of that 4 right there. And I'm going to do it by subtracting 4. Now if I subtract 4 from both sides, I now have p minus 4 on the left-hand side equals 7 square root x. Now the next thing I'm going to do is I'm going to get rid of that 7. And now since this is 7 times the square root of x, I'm going to get rid of it by dividing. So now I have p minus 4 over 7 equals the square root of x. And then my last step, if x is being square rooted, then the opposite function of that is to square it. So my last step would be my final step that gets x by itself, and it would be p minus 4 over 7 squared equals x. And I will now have the equation solved for x instead of p. The next one. 1 over w equals 1 over x plus 1 over y. Solve for w. Well, what I'm going to do is I'm going to multiply all terms. By what would be the common denominator of wxy. So that would make 1 times wxy would be wxy over w equals WXY over X plus WXY over Y. Now I'm going to reduce what I can. The denominators are going to go away because I multiplied all the terms by the least common multiple. So on this one, it's the W's. On this one, it's the X's. And on this one, it's the Y's. And I'm left with the equation that says XY equals WY plus WX. Now remember, my goal is to get W by itself, and since I've got W in two different places right here, the only way I'm going to get it to become a single W instead of two W's is by factoring it out. So I would now have XY equals, factor out the W as the greatest common factor, and you would be left with Y plus X. And now it's really easy to isolate the W because all I do is I divide both sides by the Y plus X. And I'm left with an answer of XY over Y plus X equals, over here on the right hand side, the Y plus X is going to reduce itself to 1, and I get W, and I have exactly what I want. I have the equation solved for W. Okay, let's talk graphing, since graphing rational functions was the last objective of the unit. So we start off with the parent graph, f of x equals 1 over x. The asymptotes were actually the x-axis and the y-axis. So remember, the graph cannot touch those asymptotes. And because there was a 1 up there on top of the numerator of the fraction, all we did was we went 1 over 1 up. The key point was 1, 1, which is way up here, or negative 1, which is way down there. But I'm going to do something a little different. I don't want to put 1, 1 way up there because it doesn't let me draw much of a graph. I'm going to put 1, 1 right there, and I'm going to put negative 1 right there. Now what that does is it lets me help you see what the graph is supposed to look like. It's supposed to come in and turn and do this and that. And then up here, it's supposed to come in. Remember, it never touches any of the asymptotes. So that's what the graph looks like in its parent function form. If it were negative 1, we would just be using these two quadrants instead of those two quadrants. Since we're on the topic of asymptotes, let's explore the asymptotes of this equation or this function. Y equals 3 over x minus 7 plus 8. I've gone ahead and I've drawn the x and the y-axis. Now those are not the asymptotes because we have to take into consideration the shift. Now x minus 7 means go to the right 7 units. And then the plus 8 at the end of the equation means go up 8 units. So the asymptotes are actually going to meet at the point 7, 8. Because if they begin at 0, 0, and we go right 7 and up 8, there's a very critical intersection right here. And that's the intersection of the two asymptotes. So I'm just going to draw in the asymptotes. The horizontal and the vertical. Now the horizontal asymptote, the one that goes up and down, remember I went right 7 units. and that's the vertical, it's the vertical asymptote. I went right 7 units, and that's the vertical asymptote at x equals 7. Now, I also went up 8 units, and that's where I found the horizontal asymptote at y equals 8. And those are the new asymptotes of the problem. The final problem is a very comprehensive graphing problem. It's the function 1 over x plus 3 minus 2. So the very first thing we're going to do is we're going to graph this function. Now, you can see that there are shifts both vertically and horizontally. So the x plus 3 is an indication that the vertical asymptote, which is normally right here on the y-axis, is going to shift 3 units to the left. So let's shift it 3 units to the left and put that vertical asymptote right here. And let's go ahead and label it x equals -3. There's the vertical asymptote. Now the horizontal asymptote, which is usually right here on the x-axis, it shifts down 2. So let's put that down 2, and we'll put that right here. And the equation of that asymptote is y equals -2. So we actually have the answers to these two questions. The vertical asymptote, x equals -3, and the horizontal asymptote, y equals -2. Now let's go back and talk about the domain and the range. The domain, well, let's put the graph in first. Since that's a 1 on top, I'm just going to go over 1 over, 1 up, put the point somewhere about right there, and graph as if that curve is trying to stretch out and touch those asymptotes, but it really isn't. Same thing here. There you go. There's a representation of that graph. This one's a lot better than that one, but if I try to make it more of a curve, it's just going to make it worse. Now the domain. The domain of the function is how the graph behaves from left to right, the x's. Now, it uses up all the x's, except it can't touch x equals -3. So we have to write the domain in 2 pieces. -infinity to -3, and then on the other side of -3, we go to positive infinity. Now the range does the same thing, only low to high. It would use all the reals except it can't touch -2, so we have to write it in 2 pieces. -infinity to -2 and -2 to positive infinity. Now, the next thing we're going to find is the x-intercept. The x-intercept happens when y equals 0. I think, first of all, let's figure out where it is on the graph. It's right here. Here's where the graph crosses the x-axis. So that's an important point to us. We need to figure out what that point is. So to find the x-intercept, we set y equal to 0, and we solve. So set the function equal to 0. 0 equals 1 over x plus 3 minus 2. And now we solve for this equation by moving the -2 over to the other side. -2 actually it's a positive 2 when it comes over there, equals 1 over x plus 3. And now cross multiply 2x plus 6. Remember that has to distribute. 2x plus 6 equals 1. Now subtract the 6 from both sides, and you get 2x equals negative 5. So x equals negative 5 over 2, otherwise known as negative 2.5, if you want to call it that. There's your x-intercept. That is the value of that point right there. That's the coordinate. Now, where is this graph increasing? It never is increasing. It's a decreasing portion right here, and it's also a decreasing portion right here. Okay. Where is it decreasing? Well, it's always decreasing, so all we have to do is rewrite the domain. Negative infinity to negative 3 and negative 3 to positive infinity. Now, where is this graph less than 0? Where is this graph have negative y values? Or another way of saying, where is it below the x-axis? Well, this entire portion right here is below the x-axis. So that's this part of the domain. Negative infinity to negative 3. Now, not all of this portion of the graph is below the x-axis. Only the part that starts at the x-intercept. That's why the x-intercept was an important point to find. So the x-intercept was negative 2.5. So starting from right there and going all the values of x to the right, the graph is underneath the x-axis. So negative 2.5 to positive infinity. Now the last question, where is this graph greater than 0? Well, there isn't much. It's a very small area. This graph is above 0 on the x values from the asymptote to the x-intercept. And so that's what we do. We show that negative 3 from the region of negative 3 to negative 2.5. And that's it. That's the only portion of this graph that is greater than 0.